Welcome back to the Foundry by Forge College. Okay, so if you were with us for the last lesson, we tackled identifying common deployment issues, which, is absolutely crucial because getting your code onto the blockchain is step one. But what happens after deployment? Well, that's exactly what we're talking about today. Think of this explainer as unrolling a fresh engineering blueprint to really examine the inner workings of our smart contracts. Today, we're zeroing in on gas optimization for state updates tied to Ether events. So let's just dive right in.
Now, if you're a Solidity developer, this probably hits a little too close to home. You've written this beautiful, elegant smart contract, someone sends it a tiny fraction of Ether, and suddenly, the transaction fee looks like the bill for a premium steak dinner. It's the classic developer panic. Why does it cost $50 to update a Boolean, right? When our contracts aren't optimized for stateful interactions, we just end up burning exorbitant amounts of gas on entirely avoidable aberrations. But don't worry, we're going to fix that.
Here is our blueprint to patch up this leaky gas-guzzling engine. We'll start with the gas guzzler problem itself, then apply three structural patches: the read-once memory pattern, consolidating storage rights, and packing struct fields. And then we'll wrap the whole thing up with benchmarking and equivalence testing.
All right, let's kick things off with Section 1, the gas guzzler problem.
As part of the Applied Solidity development track, you already know that getting a contract live is really just the start. Every single time an Ether transfer triggers a state update, it has the potential to burn massive amounts of gas. And to understand exactly why, we've got to look at the difference between storage and memory. Imagine storage as this deep, incredibly heavy warehouse. Every time you need to retrieve an item or put something away, it costs you a massive amount of energy, or in our case, gas. Memory, on the other hand, it's like a temporary cheap workbench right next to you. It's fast, it's light, and it doesn't cost much at all to use while you're actively building something.
Think about how a typical unoptimized contract behaves. It makes multiple heavy storage reads. It's literally like running back and forth to that giant warehouse for every single screw and bolt you need. This drains your gas tank fast, especially if you're writing to a storage slot that was previously 0, which, as we know, is notoriously expensive in Ethereum. So, what's the optimized approach? A single, lightweight memory copy. You grab everything you need from the warehouse exactly once, put it on your workbench, and get to work.
Which brings us to Section 2, the read-once memory pattern. Implementing this is actually super straightforward. It's just 3 simple steps to stop your code from exhausting itself with endless warehouse runs. Step 1. Copy your storage struct into memory. Just pull the data out of the warehouse and onto your workbench. Step 2. Compute everything locally. Do all your math, your branching, your logic right there in cheap memory. And Step 3. Write back to storage once. When the item is fully built, make one single trip back to the warehouse to store the final result. Doing all your heavy lifting right on the workbench saves significant energy.
Moving right along to Section 3, consolidating storage rights.
The goal here is to combine multiple mapping and variable rights into a single deferred structural right to save fuel. Think of this like a consolidated shipment. Instead of sending out 3 separate delivery trucks, which in our world means 3 separate expensive storage rights, just to update a user's total balance, their transaction count, and their active status, why not just load everything onto a single truck at the very end? Deferring that final right until all fields are computed is easily one of the quickest ways to slash your gas costs.
Okay, Section 4, packing struct fields.
You should really treat your data layout exactly like packing a tightly organized suitcase for a flight, to save on baggage fees. An unpacked struct might use separate massive integer fields for everything. It's kind of like throwing a single pair of socks into its own giant suitcase. It makes no sense. But a packed struct groups smaller integer types together. If you know a timestamp or a balance will never exceed certain limits, you can safely replace that massive integer with smaller ones, like a uint 128 and a uint 64. By grouping them logically, the Ethereum virtual machine can pack them into a single 256-bit storage slot. You dramatically reduce the number of storage slots consumed, and therefore you dramatically reduce the gas cost. It's a total game changer.
And finally, Section 5, benchmarking and equivalence.
Now, as engineers, we don't just slap a patch on a complex engine and cross our fingers, right? We need quality assurance. We need concrete data to prove these optimizations are actually effective. Check this out. The read once in a memory pattern, that can save you anywhere from 5 to 25%. Deferring a single write offers a massive potential drop of 10 to 40% in gas costs. and field packing can save you another 5 to 30%. If you just defer writes and combine operations, you can nearly cut your state update gas costs in half in the best scenarios. I mean, that is incredibly powerful.
But to make sure we haven't broken anything in the process, we have to follow a rigorous testing checklist. First up is the state equivalence test. You have to ensure all scalar fields match exactly before and after your refactor. Second is the gas benchmark. You want to run your tests at least 10 times and calculate the average gas saved. And third, edge case tests. What happens if someone sends 0 ether? What about a massive transfer? You absolutely need to test these boundaries to ensure things like your newly packed structs don't accidentally overflow.
Basically, you need to be 100% sure of your gas benchmarking and safety equivalence before you ever move these patterns into production. Taking this measurement-driven approach guarantees your optimizations have a real, tangible impact without sacrificing security. And honestly, mastering this kind of rigorous, 100% certain engineering is exactly what we focus on across the wider Web3 learning programs available at Forge College.
So I'll leave you with this question. On your next deployment, are you going to keep burning expensive gas on endless trips to a heavy warehouse, or will you build a sleek, optimized engine? To quickly recap our blueprint, use memory temporaries, consolidate your writes, and pack those structs tightly. In our next lesson, we'll be taking these exact optimizations and combining them with access control and reentrancy protections to form a battle-ready contract for your capstone project. Until then, keep optimizing and make sure to visit forge.college to dive deeper into this subject and discover even more Web3 resources. Thanks so much for joining me on this explainer, and I'll catch you in the next one.